Hello everyone, and welcome back to Mitchell's Physics Review. Today we will be working on capacitance. Let's take a look at our problem. Consider the circuit shown in the figure below, where C1 equals 8 microfarads, C2 equals 9 microfarads, and the potential difference equals 22 volts. Capacitor C1 is first charged by closing switch S1. Switch S1 is then opened and the charged capacitor is connected to the uncharged capacitor by closing switch 2. First, let's take a look at our setup. So, to start, we have our battery, or our change in V, right here, and we're given it as 22 volts. Then we have our two capacitors connected in parallel and our two switches. For capacitor 1, we're given 8 microfarads, and for capacitor 2, we're given 9 microfarads. Now that we have our givens listed and our picture shown, let's take a look at part A. For part A, we are trying to calculate the initial charge acquired by capacitor 1. Let's take a look at a picture for this setup specifically. We have our battery, and we have capacitor 1. Notice we're not using capacitor 2 in this situation because for this case, only switch 1 is closed. So, how will we find charge? Well, we're going to use the equation capacitance is equal to the charge over the potential difference. We can rewrite this equation and to solve for charge, plug in our two givens of our potential difference and capacitance, which is 22 volts and 8 microfarads, multiply them together, and we get that the charge on capacitor 1 is 176 microcoulombs. Now, let's take a look at part B. Calculate the final charge on each capacitor. This is a rather involved problem, so let's first take a look at our setup. We're no longer worried about the battery, but now instead the two capacitors connected in parallel by the closed switch number 2. We have C1 is still 8 microfarads and C2 is still 9 microfarads. To solve this problem, we're going to need to look at a few rules of capacitors in parallel. First, we're going to look at their charge. We know that the total charge is equal to the charge on 1 plus the charge on 2. We know that the total voltage is equal to the total voltage in 1 and the total voltage in 2. So overall, capacitor 1 and capacitor 2 will both have the same voltage, but the total charge is capacitor 1's charge plus capacitor's 2 charge. We also can't forget about our equation C equals Q over change in V, or as we rewrite it, change in V equals Q over C. So now, how do we put this all together? Well, since we know that the voltages should be equal between them, we can start by setting them equal to each other. Just find an equation that will help us solve for charge. So we can start with change in V1 is equal to change in V2. From there, we can use this equation that we derived from this one and plug it into the change in V. From there, we get Q1 over C1 equals Q2 over C2. But we only know C1 and C2, so we have two unknowns in this problem. Well, as you may see right here, this is where our second rule of capacitors in parallel come into play. We know that QT is equal to Q1 plus Q2. So we can rewrite that as QT minus Q2 equals Q1. We know the total charge from part A, in which we solved above, and we can now say 176 minus Q2 equals to Q1. Well, what do we do with this number? We substitute. So we're going to plug that in for Q1. From there, it's just a matter of algebra. We can multiply 9 by both sides and simplify until we get Q2 alone. Once we get Q2 alone, we can then divide, and we get that Q2 is equal to 93.18 microcoulombs, or the charge in capacitor 2 is 93.18 microcoulombs. From there, we can plug it back into our original equation of QT equals Q1 plus Q2. Now knowing Q2 and QT, We can plug both those numbers in to solve for Q1, which is 82.82 microcoulombs. Overall, the hardest part of this problem for me was integrating and utilizing the two rules of capacitors in parallel and the equation C equals Q over change in V, then finding a way to make them all work together and make sense to find the charge on each capacitor. I learned a lot through doing this problem. I hope you did too. And don't forget, when we have multiple unknowns, we should look back at all our rules to see if we can use something to substitute in. Thank you. Hope you have a great day.